Section 2.7 is the graphs of the tangent, cotangent, cosecant, and secant functions. And these all have denominators, so you can see why they would be different than what you would see with the sine and cosine graphs. So first we're going to graph functions of the form y equals a tan omega x plus b, and y equals a cotangent omega x plus b. And now that we've reviewed the transformations, hopefully you're seeing the transformations that are happening there. And then the second objective will be graphing functions of the form y equals a cosecant omega x plus b and y equals a secant omega x plus b. So first we're going to talk about the graph of the tangent function. Since the tangent function has period pi, it repeats every time we go another pi around the unit circle. We only need to see what the graph looks like on an interval of that length. So we know the tangent function, let's see, tangent theta is sine theta over cosine theta. So we know that the tangent function is undefined whenever the cosine function is 0. So now that we know what these cosine graphs look like, here's 2 pi, here's pi, pi over 2, and 3 pi over 2, we can see that the cosine function is 0 when x equals pi over 2 and 3 pi over 2. So at x equals pi over 2 and 3 pi over 2, the graph will have vertical asymptotes. So remember we talked about this of when do vertical asymptotes happen? When the denominator is 0. So whenever the cosine of theta is 0, the tangent graph is going to be undefined and will have vertical asymptotes. So if you plot lots of points, you'll get a graph that looks like the one in the notes or in the book. So let's look at the graph so we can see on this one period of the tangent graph what the domain is. And it looks like almost all real numbers are good, but we can't have odd multiples of pi over 2 because we had pi over 2 wasn't allowed, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on. So that looks like 2k plus 1 pi over 2. So that's odd multiples of pi over 2. So x can't be 2k plus 1 pi over 2. And remember that this is the equivalent to, go ahead and distribute and see that it's pi over 2, so that's the first time it happens, and then add pi and add pi and add pi. So either way you think about it is fine. So now notice that the range, though, this graph keeps going forever in both directions, and we get a vertical asymptote. But the range is now going to be all real numbers, because you can get every real number as the output of the tangent function, but the inputs can't be odd multiples of pi over 2. So is it an even or an odd function? If you can take the quadrant 1 piece and rotate around into quadrant 3 and you have a match, that's an odd function. The period is pi, so every time it goes pi, which this is the width, is pi, then it repeats. X-intercepts, let's see, x-intercepts are going to happen every time the sine of theta is 0. So sine theta equals 0 when, let's see, sine is 0 when theta is 0, and then pi, and then 2 pi, and then 3 pi, and so on. So x-intercepts happen when you have x equal to multiples of pi. The only y-intercept is 0, 0, which we can see on the graph. And the vertical asymptotes will happen at these odd multiples of pi over 2. So the things that aren't allowed in the domain are the same things that make vertical asymptotes. So those are vertical lines. And do notice that this function is always increasing as you read from left to right. So the graph is always getting larger and larger y values as you read from left to right. So we're going to graph functions of the form y equals a tangent of omega x plus b, and y equals a cotangent of omega x plus b. So let's see, a causes a vertical stretch or compress, a stretch if a is bigger than 1, a compress if a is between 0 and 1. If you don't have these learned yet, that pink sheet I gave you, you've got to know those. The period is still t equals, but now it's going to be pi over omega because the regular period is pi. So we divide the regular period by the omega multiplier, and omega causes horizontal stretch and compress. And however you learn this, you've got to learn it that the horizontal and vertical work differently. If omega is between 0 and 1, you get the stretch. See how it's the opposite of the vertical. If omega is bigger than 1, then you get the compress. So omega and A act in opposite ways. And B causes a horizontal shift. Oops, vertical. Forget my horizontal and verticals. A vertical shift up or down, right? Depending on if B is positive or negative. So we'll graph this function together in class. It's kind of hard to show the horizontal stretches and compresses, but we'll do the best we can. I wouldn't expect you to draw tangent to cotangent graphs on an exam because they're tricky. So cotangent, notice, is always decreasing. We could do the same analysis as with the tangent function. These graphs come up much less often than sine and cosine because there aren't really lots of things in the natural world that they describe. So let's look at the graph of the cosecant and secant functions. They're kind of interesting. So we use the graph of y equals sine x to help us graph the cosecant function y equals cosecant of x because those two are reciprocals. So whenever y equals sine x equals 0, it has to be true that the cosecant is undefined, right? So if I have a 0 in the denominator, then the function is undefined. So we also know that if y equals the sine of x equals 1, then the cosecant function will also be 1 for those values of x because the reciprocal of 1 is 1. So if the sine function is decreasing, let's think about this. If the sine function is decreasing, your numbers are getting smaller and smaller and smaller, then the reciprocal, where you're doing 1 over a smaller and smaller and smaller number, the cosecant must be increasing wherever the sine is decreasing. So remember the sine graph looks like this. So wherever the sine graph is decreasing from here to here, then the cosecant will be increasing. And if the sine function is increasing, as it is here and here, then the cosecant function must be decreasing. So the graph has to look like the blue one. So you draw the sine graph to help you get started, even though that's not the graph that we're making. And you see that everywhere the sine graph has 0, the cosecant graph has a horizontal asymptote. Where the sine graph has a 0, the cosecant graph has a horizontal asymptote, and so on. Vertical asymptotes. So everywhere the sine graph is at 1, the cosecant graph must also be at 1. And where the sine graph is increasing, the cosecant graph must be decreasing. Where the sine graph is decreasing, the cosecant graph is increasing. And when the sine is -1, the cosecant is -1, because the reciprocal of -1 is -1. So in a similar way, we can figure out what the graph of the secant of x must look like, because it's the reciprocal of the cosine. So you draw a cosine graph to help you get started. Everywhere the cosine graph is at 1 or -1, that will be a point where the secant graph meets it. Everywhere the cosine graph is 0, the secant graph will have vertical asymptotes and it will be undefined. So if we graph functions of the form y equals a cosecant omega x plus b and y equals secant a secant omega x plus b, the y is still doing a vertical stretch or compress because it's happening after the function happens, after the trig function happens. The period is going to be the same as the period of the sine and cosine graphs. And so you'll have t again is 2 pi over omega, and the omega will do the horizontal stretch and compress, and the b will do a vertical shift up or down. And we'll draw some of these graphs together, and that's the end of this section.